Assalamu alaikum and greetings. This is my first video on magnetism. Many of my colleagues asked to record magnetism, so here you go. I hope it will help you and all the others. I decided to record these videos in English, so we from Bosnia and other countries could practice a little bit of English, and all other students around the world maybe can also find these videos useful and learn something from them. In this video we will theoretically explain some basic principles of magnetism with static currents, after which we will make a connection of everything that we have learned before, starting from electrostatics, then going to the direct currents, and then to the magnetic field, magnetism. In the next few videos we will record how to solve some problems, how to calculate magnetic fields, magnetic forces, and etc. We will do many assignments and we will explain math tricks, methods, different methods, how to calculate all of these things, but in this video we will explain magnetism. When you come to the first classes of electrical engineering, you don't learn from the start what is the current. From the high school I thought I will learn first that. What is the current? No. Why? Because that is not the beginning. The current is product from something. How does the current, how do we get a current? That's not explained. So you must start from the basic, from the static. What we find in our nature, we find static charges. And from those static charges, we develop all other areas. We see how those static charges, what they produce electrical field. Then how can we use an electrical field to produce current? We find a way, and then after that we have a current. Then we analyze, okay, when we have a current, what do we get? Do we get any other field? And that's where the magnetism comes. So we will make all the connections in this video and some small introduction and explanations. So magnetism, in this video we will analyze only DC currents. Constant currents with are direct current. They don't change their polarity. Basic equations which describe magnetism with DC currents are wrote on the table. This is a differential equations, and these are integral equations. We will not analyze a lot of these differential equations. We will analyze differential equations after we finish everything. After we finish alternating currents, then we will start and analyze electromagnetism. First we will analyze electrostatic, electrical fields, then currents, then magnetism, then alternating currents, and after that we can analyze electromagnetism. And then we will use these equations. everything that we will analyze through Maxwell's equations. But that's after all of this. What we will use is these integral equations for magnetism with direct constant current. Here we have two equations. First equation says that integral over closed surface, with closed surface we get a volume, so we are analyzing some volume, do we have anything here, is equal to 0. This ds is infinitely small surface. Someone uses the notation dA, like area, infinitely small area. We will use this notation, but it is the same. Is equal to 0. What does this mean? We will see in few minutes. The second equation is Ampere's law, which says that the line integral over closed circle, so over closed loop, excuse me, when we have a line integral closed loop, we get a surface. So we are analyzing some surface here, is equal to mean magnetic permeability, constant for air, times the current. We must remember from DC current, when we work that the current is equals integral current density times elementary surface, infinitely small surface. What does this mean? It means that we have current density on infinitely small surface. Okay, this is our conductor, cross-section of our conductor. We have infinitely small surfaces, ds1, ds2. This is what this means. Differential, elementary surface, infinitely small surface. At every infinitely small surface, we have a current density. It says how much amps per square meters on this surface we have. So how will we get a current? We will get a current if we simply sum all of these surfaces. Sum all of current density for all of these surfaces. And that's what integral physically means. So this differential, this elementary surface, means I have a surface S, and I divide it on infinitely small areas, surfaces. If I want to sum of all these areas, what is the opposite of differential? It is an integral. Integral means sum of all of these surfaces. So, very important thing. What does this say? It says, now we see what is the current. The current, by definition, it doesn't say this is the current here. The current is, by definition, and I will read it. The current, by definition, is a flow of charged particles, such as electrons or ions, moving through an electrical conductor, but through complete conductor. Through complete conductor. So all electrical charges that are flowing, you sum them up, and this is the current. It didn't, for current, it's not important for this current I, it is not important, are all electrons uniformly distributed, constant through all the surface, or in this area I have more of electrons or not. It sums up all of the electrons that flows through time, and that's the of complete conductor, and that is the current. This is very important thing. Why? Before we analyze these equations, we must to know what is a current physically, what are charges physically. So, all of this is to analyze and to see what is the current. Is a current a vector? That's the question. So, first, what is a vector? Vector is everything that has amplitude, that has a line on which it has its amplitude and does have a direction. So, what does that mean? For example, velocity is a vector. I have a country, Bosnia and Herzegovina, and America, let's say, USA. And I am traveling on this relation from Bosnia to USA or from USA to Bosnia with an airplane. So I have a line segment. I am traveling between these two relations, from Bosnia to USA or from USA to Bosnia. Okay, if I'm traveling with a plane has a speed, has a velocity, v. But in order to be a vector, it must have another one characteristics. That is a direction. And that is, do I travel from Bosnia to USA with a velocity v, or I am traveling v1, let's say it, or I am traveling from the USA to Bosnia with velocity 2. This is the best example of a vector. It has its amplitude, it is the speed, it has a line segment on which we have that speed. Is it from B head to USA, and it has a direction. Another vector, now this speed, if it travels with constant speed, we can say this speed is that and that, or its speed is change. We will not analyze that, for example. Another great example of a vector is a force. I want to move this from between points A and B. Okay. Now I have a segment, line segment, point A and point B. That is one characteristic of a vector. Another characteristic, it must have amplitude. That is the amplitude density of force. I want to move it. If I move it, I can move it this way with this force, or I can move it with more force. It will move faster or less force, but I can move it in either way. So if I move it this way, it has also a direction. I'm moving it from the point A to point B, and I am moving it with force of F1. Or I can move it even faster. It will have a greater amplitude. It will be a force F2. So F2 greater than F1. This is a vector. And everything that has these three characteristics is a vector. Now, the logical question is a current a vector? And many professors ask these questions. And they say, okay, the current, it has a direction. It flows to that, from that to that. It has an amplitude, and it has a line segment. So is it a vector? You say it is a vector, and he says no, of course. But how? Why it is not a vector? Because in this definition that I told you about a vector, one word or sentence, small sentence, is missing. Yes, everything that has this, but at every point of space, it is a vector. Because of that, the current, because of its definition, it is all charges of this surface, of this space, through time. Because of that, it is not a vector. But if I come and say, at this point of space, at this surface, do I have something that has an amplitude, direction, and line segment? Yes, but if I'm talking about this small surface, I'm not talking about current. Current is complete conductor. But if I'm talking about surface, it is this current density. It has a direction of a current, it has a line segment, and it has an amplitude. How much amperes? What is the density of the charges? How much amperes per square meters? So the current density is a vector, but the current itself is not a vector, because you cannot say here what is the current, but you can say at this small surface what is a current density. The current is only for complete conductor. So in the future videos, when I say a vector source and I say a current, the current is not a vector, but I mean at the current density. We will say that it is the same. So now, we saw what is a current. We saw that the current, as the current is not a vector, but is connected with the current density, that is a vector. So we will say that current, we will often call a current a vector. So now we will analyze these two equations and make the connection between electrostatic and electric field and this. First of all, you can see here, these are from Maxwell differential equations. Divergence of B equals 0, or integral over closed surface B ds is equals 0, or curl of H is equal to current density, or integral of B dl, because opposite integral of a differential curl is line integral over closed loop, is equal to μ0 times the current, or μ0 times, this is a better to use this notation, because we see here that this right side is a vector. This is a vector, not the current. So, first two, what is B, what is H? H is a magnetic field. Unit is amps per meter. But what is B? The B is the same that we had in electrostatic with electrical fields. We had D in electric fields, which is electrical flux density. Also here, the B is magnetic flux density. And it is equal to my magnetic permeability of that material times magnetic field. So because this is a constant, when I say magnetic field, the same rules can be applied to magnetic flux density. When I say direction of magnetic field, that is also a direction of a magnetic flux density, etc. Only difference is their amplitude values in different materials. So we will make analogy to the electrostatic. In the electrostatic, we had an electric field E, and also the unit is Tesla, because of Nikola Tesla. The unit for electrical field here was ampere per meters, here is volt per meters. And like we have here magnetic flux density, in electrostatic we had electric flux density, and also it was equal to the constant which considers the material times E. And same rules were for electric field and electric flux density, only for different materials they have different values. In magnetism we have magnetic field, magnetic flux density. Here we already can see some similarities. But how these equations were in electrostatic? We won't write them. We had the same equations. We called it Gauss law for electric field. It was integral E ds, or we will use this d ds that equals volume charge integral rho dv, or q charge. Someone charge is using notation small q or big Q. We will use a big Q. Over a closed surface S dds is equals this. Or you can also write this equation with the electric field E, where we will have epsilon 0 or epsilon L, but it's enough to use this notation. We can explain electric field with the same equation as a magnetic field, with same mathematical operator. It means they are similar. But what we get here? Here we have that this integral is equal to something, and that something is a charge, and that charge is a quantity. It doesn't have polarity, direction, intensity. It is a quantity. So much charge at one volume, at one place, and that's it. It is not a vector, it is a scalar. But here we have the same that equations for magnetic field, but it is equal to 0. What does this mean? It means this mathematical operation, integral over closed surface S of a field, whatever that field is, here we are analyzing electrical and magnetic field, is equal to scalar, and it tells us what is the source of this vector. In this formula it says what is the source of an electrical field. Here it says what is scalar source of a magnetic field. The same is here, differential. So divergence or source tells us what is scalar source of this field. And here we got that electric field has scalar source Q, which is electrical charges, but the magnetic field doesn't have a source. What does this mean? Here we had that electric field has a source which is charge, and we said, okay, Q, let's say positive charge. If it's a positive charge, that means it is a source. It starts here and ends somewhere. and this is an electrical field or electric flux density, it is the same. And we know this, we learned this. So it has a source, it comes from a closed surface. It says this field has a source from a closed surface. If it is a negative, of course, the magnetic field here is minus. The magnetic field is minus, so it's not a source, it is a sink. The electric field ends here. It goes inside the negative charge. So we have a start and goes, it's a source from some volume and goes outside. But here it says that the magnetic field doesn't have sources from the closed room, from some volume. So it cannot it is not, so this means it doesn't have a source. It means it doesn't have a beginning or end. It doesn't have a beginning from some volume, from some scalar source. So what does it mean? It means this magnetic field is closed, makes a circle. His lines are closed inside itself. This is what it doesn't. You cannot say here it starts. No, the lines are closed and started. This, it doesn't have a source. Those are closed lines. Closed line. So this is the magnetic field. It has this type, not this type, but this type, because it is equal to 0. It says it doesn't have sources. It doesn't have scalar sources. But what creates magnetic field? What type of source then? Then this other equation, Ampere laws, says that the line integral over closed curve is equal to the current density, or to the current. So this means that this equation tells us what are a magnetic vector sources of this field. Or if you analyze the Maxwell equation, what are the vector sources of this field? So the magnetic field doesn't have scalar sources, but it does have a vector source, which is a current or current density. So, which means if I have a conductor with a current E or current density J, every time this current, it says that this current will create, current flux density will create a magnetic field. How does this magnetic field look? We already draw it. It's the circles around this conductor. If we want, what can we see here? We can see that the magnetic field changes its direction at every point. So how can we determine the direction at some point that it is interesting to us? We want to calculate at this point. But because it's a circle, it is a line, it is a circle, always for circle the direction is determined with a tangent. Tangent presents the direction of a magnetic field. So, if we want the direction of magnetic field here, and that means that magnetic field is a tangent at this point, its amplitude presents this length of a vector, and this is the direction. Line segment is the complete circle. So, if we want a magnetic field here, it is a tangent here, so this is the direction. If we want it here, so the tangent is here, and this is the direction of a magnetic field. But how do we determine this direction of circle? Is it this way or is it an opposite? This is determined with the right hand rule, where you put your thumb in the direction of a current and your closed fingers, you can see in which direction you are closing your fist, your fingers, that is the direction of a magnetic field. We see that I'm closing this way, so this is the direction of a magnetic field. If I have a current through a conductor, then the magnetic field I must right hand, remember right hand, not left hand, I must this thumb direct in the direction of current, so the direction of current is up, down. So if I put this thumb down, I can see with my fingers how did I close my fist or my fingers. It is this direction. So in this way I will get this direction of a magnetic field. B or Then it is very important to know at which side do I need to calculate a magnetic field. So if this is a surface, let's say, so this is my conductor, I have a magnetic field around it, and I'm analyzing only this area. This is what I draw. So this surface where I put my conductor, it means that magnetic field at this point can be, it is a normal to the table, and it can have a direction from the table or from you to the table, or from the table to you. It can have, because it is a tangent, it can have direction from table to you or from you to the table, like here. So this is that surface parallel, and here it has a direction from you to the table. Also other notation, how can you describe this? You can use it like this, like the arrow. If it goes from you, you are seeing that X, and if you need to calculate a magnetic field here, then this is my conductor, magnetic field tangent at this point is to you, from the table to you, and if you see the arrow, you will see the point going to you. So we saw this similarity. We saw how do we determine the magnetic field, its direction, and such. In the next videos, we will show you the methods how to calculate these magnetic fields. But still, we didn't explain how did we get a current. What we first learn, we learn at Faculty of Electrical Engineering, we learn this. Electrostatic, I have static charges, they create electric field. But what happens? How from this I get a current? We know that if I have external electrical field, let's say I will draw it like this. I have positive charges here, and I'm making constant magnetic electrical field. These are the negative charges. So it will create an external electric field. What happens if I put my conductor in this electrical field? So I will draw it like this, simple. I put a conductor in this electrical field. What is the main characteristic of a conductor? The main characteristic is that it has a lot of free charges. Charges can be positive charges or negative charges like electrons. It has a lot of free electrons. So it has negative charges, positive charges, a lot of free positive and negative charges. What happens when I have a charge, positive or negative, in electric field? Then let's remember from electrostatic, on those charges, charge Q, we will have a force which will move these charges. So if I have a charge in external electrical field, in an electrical field, free charge, we will have a force on this charge. So these electrons, negative and positive charges, will be moving. They will move. If I have a constant electrical field, those charges will have constant movement. Constant movement, any movement of electrical charge produces the current. If this field is constant, this movement will be constant. It means that we will get a constant current. And that's where the magnetism starts. After we get a constant current, then it says, aha, okay, we have a magnetic field now. If this field is not constant, then it changes. Then the movement of these charges will change. So the current will not be a constant. It will change. So our field, magnetic field, will not be constant. It will change in time. But for now, we will analyze in the few future videos, we will analyze only magnetism, static magnetism, with constant currents. But let me explain this to the end. How will this move these charges? What will be the direction? Here, direction of electric field, the source is positive, the sink is negative. It starts from the positive, it ends at the negative charges. This is the direction of our electrical field. We have equation here, and we will follow the equation. It says if a charge Q, it can be positive or negative. If it's a positive, the force will have the same direction as our electrical field. So all these positive charges, and I will draw it on the same one, will tend to move to this side. So the force will have the same direction as an electrical field. So they will tend all to move to this side. Plus, plus, plus. All positive charges will tend to move to this side. And what if we have a negative charge? Same amplitude. Then we will have minus Q times E. So this force, in this case, will have an opposite direction from the direction of our electrical field. So all negative charge will be moved to this side of a conductor. This way, if we create constant electric field, this movement will be constant. well, this conductor is closed, it has if you close this conductor, not open circuited, then this current will flow as long as we have this electrical field. And that's how you get a current. If I want different change of current, I will create a different external electrical field. But what happens here now? Now all the rules are always there. We must follow them. Now we got positive charges here, negative charges here. Whenever we have a positive negative charge, it creates its own electrical field. So this will create this type of field, this will create this type of field, so it means this field will be this way. Now these charges which moved will create their own electrical field. So this is electrical field of charges inside a conductor. Look at this. Now, what is the direction of this electrical field? It is the opposite from the external electrical field. So, this electrical field created external electrical field, so it is opposite. What is the amplitude value of this electrical field? This electrical field, E charges, the amplitude must be the same as an external electrical field. So that the resultant magnetic field inside a conductor, E resultant, inside conductor, as you have learned and now remember, is always equal to 0. Why? Because of this. I have this external, I also have inside this, which is the opposite direction, so the resultant electrical field, E charges plus E external, is equal to 0. Why? Because E charges is minus E external inside the conductor. So this is why you have learned that the electrical field inside a conductor is always at 0. Of course, we don't have ideal conductors, but we are talking about that in practice. But why this electric field must have the same amplitude? Because if it didn't have the same amplitude, that would mean that if it has a bigger amplitude, for example, that would mean that I have made up an infinite source of energy, perpetuum mobile. But naturally, I cannot have an input smaller than the output. I cannot have output bigger than the input. If I had that, then I would have a perpetuum mobile, infinite source of energy. By nature, it confronts, this electrical field confronts from its source to its source. That's why this field must be the same. In other words, I would put a little bit of energy and I will get a much more energy. And that's unfortunately impossible. Here and now. Maybe in the future, who knows. So, that would be it. In the following few videos, we will see how can we calculate this field, and it will be, we will use Biot-Savart's law, and after that we will go wider and wider. This first lecture is only theoretical, but all following lectures are calculations showing how to calculate, how to solve problems. Thank you very much. The video was long, but I hope that you learned something new. I tried to connect to you why do we learn first on electrical engineering static charges, electric field, then how the current we get, and then what happens when we get a current. And we are at that point. We get a constant current. Constant current creates magnetic field. Now we will analyze this magnetic field, the methods, how to solve it, what forces do we have, etc. Then the next step, logically, would be what if I don't have here a constant electrical field, if I have alternating electrical field which changes in time and maybe changes its direction. When we come to the Faraday's law, we will come to that point. And from that, we will analyze, okay, then that changing electrical field will cause a changing current. Then what happens when I have a changing currents? Do my equations change? Do I got a dependence from some field, etc.? That we will analyze in the near future, I hope. Thank you very much and best regards.